Hey, we are going to start on page 13 for today. I want to talk about a couple of the problems that you guys saw for homework last night. Then we're going to take a look at another graph story problem, same sort of types of questions and setup as what you had for homework, just another example. We'll take a look at a couple extra examples that are not in your packet, and then we'll have a quick check over our graph stories, interpreting information from a graph. And then we're going to end class today with a quick little review of some things that we should know how to do on our calculators. So that's what we've got for today. Again, we're starting on page 13. This, again, was your homework for last night. So on page 13, I want to start by talking about number 1. Number 1 says, what does the point 4, 9 represent? So if I want to know what this point means. So essentially what we're doing here is like assigning the labels to the X and the Y, right? So I know 4 is the X, so I want to make sure I put the X label on there. So 4 minutes. And then Y is 9, so it'll be 9 calories per minute. And then I just need to add in the terms I need to make it a sentence, right? And the way we can structure these descriptions may vary a little bit. So if you don't have exactly what I have, that's okay. But we should have something like at 4 minutes, the person is burning 9 calories per minute. Anytime we're interpreting a point in the context of the problem, that means that we're essentially going to make sure we've assigned the correct labels to the X value and the Y value, okay? You could have also had the person is burning 9 calories per minute at 4 minutes. So kind of flipped, as long as we've got 9 calories per minute and 4 minutes as our sort of mark on how far we are into our workout on the treadmill. Questions on number 1? Let's hop down to number 5. Number 5 says, when is the person burning the highest number of calories? What do I want to look for on the graph there? So we want to look for the highest point on the graph, you're right. So the highest piece of our graph would be this section right here, right? That would be the greatest number of calories. So it's not like a maximum or like a sharp peak. That's okay. We've got a sort of a plateau looking thing here, a flat top for our highest calorie burn. That's okay. But I want that highest Y value because Y tells me how many calories I'm burning. So for number 5, when is the person burning the highest number of calories? That would be from 16 to 20 minutes. From 16 to 20 minutes. That makes more sense because you told me highest point on the graph and then you gave me a value that was not the highest point on the graph. Total minutes on the treadmill for number 2 would be 24 minutes. Good. And then let's take a look at number 6. What is happening between 4, 9 and 12, 9? So that's this section of our graph right here. What's happening there? They're what? They're not moving. I have some. They're using a constant pace. Now, if no calories are being burned, that means this should be down here at 0. Okay, so this is keeping track of how many calories we burn per minute. So this is only tracking for an individual minute. So from minute 4 to minute 5, we burn 9 calories. From minute 5 to minute 6, we burn 9 calories. Does that make sense? So you guys who are saying we're burning calories at a constant rate, that's what's happening here. And then at the end of the question, it says, is the person standing still? Are we standing still? Okay, so they're not standing still. If they were standing still, we would expect their calorie burn to drop down to its sort of initial level, right? If I wasn't moving anymore. What we can see here is that we keep our calorie burn at this sort of elevated level. And it's not the maximum calorie burn that we've had. So maybe here is we're running flat out as fast as we can. And here is where we've got like a brisk walk or a jog happening. So we're moving at some sort of constant pace. The person is moving at a constant pace. Okay. I mean, you can shut, depending on the treadmill, you can shut it off and just stand on it. So be careful with adding more to the question than it's asking, okay? So for like number 2, it says how many total minutes is the person on the treadmill? That's what we've graphed here. And so they start at 0, and then we have a final point here at 24. Even if they were standing still for a period, we would still count that as how many total minutes were they on the treadmill. If our question was for how many minutes are they moving, then that's where we would eliminate any chunks of time where we could see they were standing still. Does that difference make sense? Okay. Are there other questions from your homework on page 13 that we need to talk about? Anything else you guys want to go over from page 13? Okay, go ahead and turn the page. We're going to take a look at another example on page 14. So we've got a graph here at the top and then some questions we're going to answer. For page 14, this is a car is traveling on a straight road. The car's velocity over time is displayed in the graph. So time in seconds is our x-axis, and then velocity in meters per second is our y-axis. Number 7, similar to the first question we asked on the last page, what does the point 16, 20 represent? So that would be this point right here. 16, 20. So if I take a look at the sort of general path, I can see that's the end of this period where they've maintained a constant velocity. Good. If we pull away from looking at that general, and I want to know this point specifically, what does it tell me? Meters per second. Yeah. So we had 2 really good answers here. One sort of looking at the big picture of our trend of what's happening. At that point, I'm changing my velocity because it's sort of the end of this plateau that we've got here. Specifically, which is what I'm going to jot down for number 7. Specifically, remember this is an x value, this is a y value. To interpret this point in the context of the problem, I'm essentially tacking on those labels here. So at 16 seconds, the car is moving at a velocity of 20 meters per second. And if you phrase this a little differently than I did, that's okay, as long as your labels are appropriate. 16 seconds and 20 meters per second as our velocity. Number 8. So this is kind of a bigger picture question. What's happening between 4, 20 and 16, 20? So what's going on here? Somebody I haven't heard from yet? we're at a constant speed right there. We're maintaining a constant speed. The car, or velocity, I should say, is maintaining a constant velocity. Our car is maintaining a constant velocity where I've got that plateau. Cool. Number 9, what's the y-intercept and what does it represent in the context of the problem? Remember, y-intercept is where we cross or touch the y-axis. Yeah, so this one is maybe a little tricky. I had a couple people earlier today say, I don't know if that's really 0 or not. The slope's pretty steep here. I think it looks to me like we're going to cross right at the origin there. And that's what you said as well. So I'm going to go with 0, 0. So our y-intercept is 0, 0. And then will you give me your, what does it represent in the context of the problem piece again? Yeah, so this is a time of 0 seconds. Our velocity is 0 meters per second. So you could phrase it just like that. At 0 seconds, the car has a velocity of 0 meters per second. Sort of follows how we wrote number 7. We could also, though, take that one step farther and say 0 seconds would be the beginning of us looking at this car's velocity. So I could say at the beginning, the car is, and again, I could say moving at 0 meters per second, but am I moving if my velocity is 0 meters per second? No. So what's another way maybe I could phrase that? The car is stopped. Yeah, the car is stopped. When is the car speeding up? What does that look like on our graph? When is our speed increasing? From 0 to 4 seconds, where I have this positive slope here. When is the car speeding up? From 0 to 4 seconds. When is our car slowing down? Where I have this negative slope from 16 to 24 seconds. Now let's talk about x-intercepts. So we said when we talked about number 9 that the y-intercept is where our graph crosses the y-axis. So when x-intercept is where our graph crosses the x-axis. So where do I have x-intercept? Yeah, at 0 and at 24. So I've got an x-intercept at 0, 0, and I have an x-intercept at 24, 0. What do those points represent for our problem? The car is stopped, right? At these points, we have a velocity of 0. So this represents when the car is stopped. The car is stopped at 0 and 24 seconds. That's when our car is stopped. And then our final question here on page 14, how long is this car in motion? How long are we moving? Yeah, here it starts at 0, it's moving, it's moving, it's moving, it stops at 24 seconds. So we're in motion for 24 seconds. Questions for me on page 14? Okay, I have a few extra examples that I would like to take a look at. These are not in your packet, so they're just going to be up on the board here. Just a couple extra practice problems over our graph stories. So for the first one that I have here, I've got 4 different options for stories, for scenarios. I want you to take a minute, read through them, and tell me which could match this graph. So take a minute, read through those 4 different scenarios, and I want you to tell me which of those you think could match that graph. Let's take a look at our graph first. So our x-axis is time, our y-axis is distance. So as I look at what's happening here, over time, my distance goes up, then my distance comes down a little bit. Then what would this flat part here represent? Distance is, I'm sorry, what? Yeah, our distance isn't changing. That means we stayed in the same spot. And then our distance goes all the way back down. So if my distance started at 0 and ended at 0, that would mean I went back to wherever I started from. Okay, so I went away, I started coming back, I stopped, and then I came the rest of the way back. So let's take a look at these scenarios. A, starting from home, Kyle jogs, increasing his speed until he gets a cramp. Then he slows his pace, begins walking, and returns home. Does this match what we see in our graph here? No, right? Most notably, we don't have a stop anywhere in this scenario. It talks about the speed changing, but never about him stopping. Let's take a look at B. Starting from home, Kyle rides his motorcycle to the lake and stops for a swim before returning home. Does B match what we see here? He stops in B, but why is that not the same? What would B look like? Yeah, B would look like he goes to the lake, he has a swim at the lake, he comes straight home. That's not quite what we have here, so it's not B. C, starting from home, Kyle rides his motorcycle to the lake, then turns around and returns home, stopping for gas on the return trip. We like C? C looks good to me too. I drove to the lake, I started to come home, I had to stop for gas, and then I came the rest of the way home. And then let's look at D. Starting from home, Kyle rides his bike up a steep hill, then rides down a hill. He crosses a bridge before he returns home. There's no point where he stops in D. It talks about the different terrain that he encounters, going up a hill and down a hill and over a bridge. But this is distance from his home, not elevation, right? So this kind of looks like I went up a hill and down a hill and then, but that's not what my labels are representing here. So this would have to be C. Let's talk about the second one on here. The graph at the right shows Dylan's motorcycle trip from his home to his friend's home in another city. During which time interval did Dylan stop for lunch? What section on this graph would represent that he stopped? Between 2 and 3 hours. Yeah, my distance isn't changing between 2 and 3 hours. During which time interval did Dylan maintain the fastest average speed? When's he going the fastest? You say that for me again. From 3 to 5? From 1 to 2. So from 3 to 5, and then from 1 to 2 are the ones that we have in question. How will I know when I'm going the fastest? I'm looking for the steepest portion of my graph, okay? So from hour 1 to hour 2, I cover 50 miles, right? I'm at 25 miles. and then I end at 75 miles. From 3 to 5, I cover also 50 miles, but it takes me 2 hours to do it there. So this section here would be our steepest portion. So that's where we're going the fastest, between 1 and 2 hours, or between hour 1 and hour 2. And then what's the total distance that he traveled? How far did he have to drive to his friend's house? Yeah, 125 miles. The end of our graph is 125 miles. I've got one more problem for you. This is sort of a reverse of the first one on this extra set. So this time, instead of one graph and you pick the scenario, I've given you a scenario and I want you to pick the graph that best fits this. So here's our scenario. It says Allison walked from her school's common area to her math class. After class, she walked back to the commons area, stopping to get a candy bar from a vending machine on the way. Which of these graphs best models the scenario that we've got here? See? So we're measuring distance from the commons over time. So she walks to her math class. She's in math class. That's why her distance doesn't change. Then she starts heading back to the commons, stops at the vending machine. So again, distance doesn't change again, and then walks the rest of the way back to the commons. What's the problem with A? Why is A not a good fit? Yeah, she doesn't stop at the vending machine. We don't have that second stop here. What's the problem with B? She didn't go to class, right? I mean, she walked to the door and then turned around. She's actually got to go to class. Okay, very good. Okay, I would like you now to please put away everything besides a writing utensil. You have a short quick check over graph stories. You don't need a calculator. Okay, just a couple of reminders. Remember, anytime that I hand you a quick check or a quiz or a test or whatever the case may be, I'm looking for your work. Make sure you're completing your own work. Once you're finished, you're going to turn these into the folder labeled 8th hour over here. Okay. Make sure you put your name on your paper. There isn't really work to show on this one, but just as a general reminder, when you're finished with your quick check and you've turned your paper in, please get your notes back out and open up to page 15. On page 15, I want to review some calculator skills with you guys. Last year in geometry, it's my understanding that you used your calculator to help you with some computations, but not really for much else, because you wouldn't have needed it for much else in geometry. So last year, you probably squared things. You probably used the square root key. You probably used the pi key a couple of times. And you probably maybe used your scratch pad or a calculator document to help you simplify things like 2 times 18 plus 75 or something like that. And you use some trig functions too? Okay. In algebra, we're going to use your calculator more than you did in geometry, and we're going to use it in a little bit different ways. We're going to use some different functions on here. I'm going to put my calculator up on the screen that I'm projecting to you guys, so that way we can all see what it is we're looking at here. And I'm going to add a calculator page in a document. Everything that we're going to look at today, you could also do on a scratch pad. However, there will be a few times throughout Algebra 1 where we need functions that aren't available on Scratchpad, and we need a full-blown calculator document. If you're working on Scratchpad for today, that's fine, but I just want to give you that disclaimer that we do know we will need a calculator document page for some of the work that we're going to do later on in Algebra 1. So on page 15, I'm going to start by looking at number 1. Number 1 is 3 to the 5th power. So you guys used the square button last year, I'm going to guess, in geometry. That's that key where if I hit this button, it just makes whatever I have squared to the 2nd power. But if I want a different exponent, I need to use a different key. So if we want 3 to the 5th power, I'm going to type 3. And then do you see this key right here that kind of looks like a little mountain? That's called a caret. And if I hit that key, it gives me the ability to type in whatever exponent I would like. So for number 1, we want 3 to the 5th power, so I'm going to type a 5 in there. Now later on, as we're typing in exponents, we may have a problem where we have 3 to the 5th, maybe plus 8. And so if I hit my 3 to the 5th, and then I want to include the plus 8 part of it, if I type that right now, see how it shows up in the exponent? This is something that has happened more than a few times in Algebra 2, where we're trying to graph something and we type the whole function in an exponent, and then you have to regraph the entire function or re-enter the entire function. So just be careful with that. I have to, if I want to no longer be in the exponent, I have to arrow out of the exponent. And now if I needed to add things, I could do that, but just something to keep in mind, okay? Be careful. Remember, your calculator is not as smart as you are, okay? It needs you to tell it explicitly what to do. So for 3 to the 5th, I type 3 to the 5th, and then I'm going to hit enter, and there's my solution, 243. Let's take a look now at number 2. I know there are 2 number 2s on your page, so I'm going to do the number 2 across the top of the 2nd column, and I've got 3/7 times 2,534. There are several different ways that I could access most of the features of my calculator, most of the commands that I would want. For a fraction, probably the easiest option is to hit that blue control button and then divide. Oops, that wasn't it. Hit the blue control button and then divide. There we go. So now I can type my fraction, 3, and then I'm going to arrow down to get to the denominator over 7. And then the same as our exponent. If I type now times 2, 5, blah, blah, blah. See how I'm at the bottom of that fraction? I need to arrow out of that fraction. So just be careful with that. I bring it up because these are mistakes I see pretty frequently, and then we don't understand why we have crazy numbers. So just be careful with these. So 1,086. If at any point you type something into your calculator and you don't get what I get, please let me know. It probably means we have a setting issue that we need to adjust. Everybody with me so far? Okay. Moving on to the next number 2, the one that's below number 1, which I believe should have been number 3. We've got a square root there. You guys use the square roots in geometry, right? Probably Pythagorean theorem problem. Yep. Okay, so I know it's hard to see up here, but if you've forgotten where the square root key is, it's hard to see on the board because it's very tiny. But if I hit the blue control button and then that x squared key, there's a little square root right above it, sort of right next to the 4 button there. So I'm going to do the blue control button. And then that x squared gets square root, and I think we're taking square root of 28, right? 28, enter. And our directions on page 15 say to round answers to the nearest thousandth. So that would be 3 decimal places. Did anybody not get 4 decimal places on their calculator? Anybody not get 4 decimal places? Okay, perfect. The decimal place issue is a common settings adjustment that we may have to make. So if at any point you don't get the same number of digits that I get, please let me know. It's an easy setting to fix. But if we don't fix it, you may get some slightly different answers. So if I round this to 3 decimal places, I would get 5.292. And then let's take a look at number 5. Number 5, I have 5 over 6. I have a fraction there that I want to approximate. That's what that squiggly equal sign means. What is this approximately? So what would it be as a decimal? How can I change a fraction to a decimal on my calculator? Divide the 2 numbers. So 5 divided by 6 and hit enter. It spit out 5 over 6 again. There's a couple options here to change a fraction to a decimal. One of them is to type in what I have for my fraction, 5 divided by 6. And you could do control divide to enter it like a fraction like we did earlier, or you can just treat it as a division problem. But then if I hit that blue control button and enter, see right above the enter, it's got the squiggly equals in blue. That's telling me to approximate. So 5 over 6 and then control enter will give me a decimal approximation. There's another pretty quick option. Yeah, the other pretty quick option is to just put a decimal in your number somewhere. This is what I pretty frequently choose to do. So if I do 5 over 6 and then just put a decimal after 6, you could also put it after the 5, that's fine too. But if I put a decimal in my problem that I type in and hit enter, it will give me a decimal as an answer. And same number of keystrokes for either of these. Questions for me so far? Okay, I would like you now to try number 7, number 8, number 9, and number 11. 7, 8, 9, 11. I'm skipping the pi problems because pi isn't a number that we use a lot in algebra, so I'm not so concerned with you guys remembering how to find pi. I know you used it a lot in geometry, but we won't use it very much in algebra. Okay, let's finish up here. What do we get for number 7? Perfect. Round to 3 decimal places, we should get 0.563. How about number 8? 380. Number 9, 8.660 if we round to 3 decimal places. And then number 11. Perfect, 0.875, very good. Please make sure you bring your calculators tomorrow and that they are charged. If it's not charged and it doesn't turn on, it's not a calculator, right? It's just a heavy thing you have to carry in your book bag. So please make sure your calculators are charged and bring them tomorrow. The first thing we're going to look at tomorrow is a review of how to graph on our calculators, okay? That will be something we use pretty frequently in Algebra 1. So we're going to take a look at that tomorrow.